All right, today we're going to do Laplace transforms or not Laplace transforms, we're going to continue with Laplace transforms and continue on with the inverses. So, past three lectures have been what are they, what are they useful for, how can I find them, and then we kind of had our common Laplace transforms. It was almost kind of like having a derivative table. And I said if you read it backwards, you had the inverse Laplace transform. So they're kind of analogous to the inverse Laplace transform, is almost like an antiderivative. And there's going to be a very specific reason that I use antiderivative and not, say, multiplication and division. So this transformation that we've seen and know and have beaten into our minds at this point, typically we're going to be looking at second order differential equations, and they'll be equal to a function. And then once you do the Laplace transform, then the goal is to say, okay, well, now I have everything mapped to this t domain, or from the t domain to the s domain, where the s domain was algebra versus the t domain were these differential equations. And then saying, okay, after I've solved all this, how do I come back from it? So right now we're just going to say, here's x of s, then, or capital X of s, then what's x of t? So the method would normally go, use the Laplace transform, gather all of your terms, then you would get x on one side, and then look at what was left over and say, okay, well, then what would my Laplace transform be? So like for this one, this was like our phase shift. So we knew that from this one, if I had e to the 5t, that would be what my original function was. So basically this is what we're going to do today, is some practice with how do I go backwards. And a lot of it will be just kind of looking at a function and trying to rationalize, might not be the best word, but kind of try and figure out what do I need to get out of this. And say, here's the function, how do I go backwards to where my actual solution lives? Because the Laplace transform domain, the S domain, is, again, it takes differential equations to be algebra problems. You play with them in there, you get them solved, but you don't leave them there because that doesn't answer our differential equation question. So getting back is going to be very important. And again, to reiterate, it's very analogous of the differentiation and integration argument. And I'm very keen to use that argument, not, like I said, not multiplication or division or addition and subtraction, because there's going to be a specific reason where it comes up. So what is the Laplace transform? Or what did I do the Laplace transform of to get 7 over s to the 4th? Well, break it down into, first of all, what does it look like? Well, first off, it kind of looks like a trig function. More specifically, as you can see, it's going to be sine. Because if we did sine of kt, we did our Laplace transform of that, it's k over s squared plus k squared. But our issue is we don't have s squared plus 4, or we have s squared plus 4 as the denominator, but we don't have a 2 in the numerator. We've got a 7. So the question is, okay, well, what do I do now? So first things first is, you don't have a 2, doesn't really matter. Hardest thing you ever do in math is multiply by 1 and add 0. So that's what you get to do here. Because basically what I'm saying is, another way to think about this is to multiply the front by 2 over 2. And then because it's linear, I can factor out constants. And because of that, really what we're doing is we're getting these two to swap places. And so by linearity, I'm left with 7/2 out front. And now I have the inverse Laplace transform of 2 over s squared plus 4, which we know is the Laplace transform of sine of a constant times t. So thus, we have our inverse Laplace transform. And all it took was knowing what the Laplace transform of sine of t was, or sine of a constant times t. And then taking advantage of the linearity property. The hardest thing, and probably the least obvious of all, is the multiplying by 2 over 2. A lot of times you're going to have to kind of force these problems to be what you want. So instead of just saying, well, it doesn't look like I want what I want, I guess I just give up and go home, you have to kind of work with them a little more. That's why I said, like, completing the square is going to be, or on that title slide I had completing the square and partial fractions. Because sometimes it's about reducing these problems to a more common form. Kind of like if you want to do the integral of sine squared, it's a lot easier to use your power reducing formula and get it in terms of something that doesn't have that sine squared part in it. So kind of like trig identities, it's just kind of moving things around to be what I need them to. And this is one thing that I kind of breezed over. The Laplace transform is linear, so if the inverse exists, it also too has to be linear. So like a Laplace transform is linear, the inverse of a Laplace transform is also is also linear. So we can use all those very nice techniques to work out some problems. And the reason I say that it's nice is if I'm trying to do the inverse Laplace transform of f of s plus, I should use capital letters since that's what we typically lean for. So if I was doing the inverse Laplace transform of these two functions, then I know that it's just the sum of those Laplace transforms. So it makes it easier. Now, this is it looks almost like a footnote, but it's very important. So if there exists a continuous function such that Laplace transform of f is equal to capital F, then we define the inverse Laplace transform of capital F is lowercase f, and this function is unique. Maybe I need to emphasize this. A continuous function has a unique Laplace transform. That's going to be key here in a minute. So maybe it doesn't equal a continuous function. What if the initial function had some sort of discontinuity? So take, for example, the function that's 1 between 0 and 1, and then it's 0 after you get past 1. So do the Laplace transform of the piecewise function. You get your first piece. You use that same domain. But the nice part is, because it's 0 after you get past 1, it just goes away because it's multiplied by 0. So then you're just left with doing the integral of e to the negative st and evaluating it from 0 to 1, which gets you this Laplace transform here. Now here's a weird thing. What if I define this function where it's basically the same piecewise function, but now at t equals 1, the function value is 18. So notice we have very similar components. I'm not going to do a bunch of underlines because that'll get even messier for this one. But the thing is, I do want to emphasize this part. 18 t equals 1. Because it's only at 1, when you do this integral evaluation, you're taking the derivative of an infinitely, or you're doing the integral of an infinitely thin strip. So this is kind of like when you talk about integrals on closed or open domains, one single infinitesimal is not going to change this problem, because the integral from 1 to 1 is 0. Same way this integral is 0. But the key thing is that front part, the integral from 0 to 1 e to the negative st, is the same thing here. So 1 over s e to the negative s over s. So your question is, what's the Laplace transform? Is it f of t or g of t? So in this case, you kind of just don't really know. What we're missing, and this is kind of going to be important, you would need some sort of initial conditions. Because if you don't know, because kind of right now, this is the situation I was talking about and why I kind of made the comparison to antiderivatives. Because when you do an antiderivative of a constant, you get, so 1 for ease of example, you get t plus c. That's your antiderivative. But the question is then, is it t plus 17? Is it t minus 3? Is it t plus 230,000? You don't know. You need that initial condition. So if you were to do this at the start, you would probably just more so default to f of t, because, well, you really don't know what's going on. If you had that initial condition, though, that t had to equal 1, then you might be able to go back a little bit easier, because you can look at this one and go, oh, 1 over s e to the negative s. I could kind of think about this as the same as like e to the 0 or e to the negative st over s, that being evaluated from 0 to 1. So it's kind of like looking at that snapshot and trying to figure it out. So you can think about this as e to the 0 s. But you would probably lean towards, without any prior information, that f of t. But it could be g of t. Notice the whole point of that theorem was, if the original function is continuous, then the solution is unique. So if the original function is not continuous, you're not guaranteed that unique solution. So this is why I say you probably would need an initial condition. Otherwise, you're probably going to lean towards f of t without any of that other context to help you out. So if there exists a piecewise continuous function such that Laplace transform of f of s and f of t, and f is unique, this is the key thing. up to the values at any jumps in the function. So this is why anytime you could technically go through here and say, well, I can make another one. So like I could add in, just for example, I could do h of t, and it still has, it's 1, 0, less than t, less than 1. I could do 18 if t equals 1, but then maybe it's 0 if 1 is less than t, which is less than 30. And then I could say that it was 17 when t does equal 30. And then also go right back to it's 0 if t is greater than 30. The whole point of that is saying the key is it's still made up of 1 on the interval 0 to 1, and 0 pretty much kind of onward. It just has these weird kind of discontinuities. So it's going to be unique up to the value at any jumps in the function. So a Laplace transform inverse cannot take into account those jumps without kind of having those initial conditions. So if there was a jump that occurred, then you'd be able to say, oh, well, if you knew what the function was at the time the jump occurred, you could actually sort it out. But because of most functions, you probably won't be able to. You'll be able to get a general function, but you would just say, this is the inverse Laplace transform up to any discontinuity. Now the nice thing, so to translate or transition to something a little bit nicer, what if you do the Laplace transform, or we talked about the Laplace transform of e to the alpha t times a function was the same as just doing at. I keep saying alpha. Then that would just be the phase shift. So if we take into account this problem, so s minus 6s plus 13. If we first look at this doesn't look like anything we have. It looks, I don't know. We don't have anything that's like 4 or a number over this plus this. Now we could try a partial fractions here. However, what multiplies to get 13 and adds to get negative 6 is probably not going to have the nicest of roots. So let's try and avoid that if at all possible. This is where we start to bring back some old algebra techniques like completing the square. So if I were to do the inverse Laplace transform of 4 over s squared minus 6s, and then as a quick refresher, to figure out what you need to complete the square, it's divide the the middle term, which since we don't actually have a term, multiply the coefficient of your variable to the first power, multiply that by a half, and then square it. So in order to make this a perfect square, or a perfect squared trinomial, I would need to have s squared minus 6s plus 9. So what I'm going to do is just kind of, I'm just going to split the 13. I'm just going to borrow from it. Now this would be a case if you didn't have enough, you would just say add 0, where you would say, oh, I need it to be 9. The other way would be to say add 9 and also subtract 9 at the same time. So this would have been the other option. So to have s squared minus 6s plus 9 minus 9 plus 13, which if you notice still gives you the 4. So now that leaves us with the inverse Laplace transform of 4 over s minus 3 squared plus 4. Now we're kind of getting really close to our original idea. This almost looks like the sine of t function, but we have a 4 up here instead of a 2. Just like before, make this 2 times 2, factor one of those out, and now we're left with 4 over s minus 3 squared. Oh, not 4 over. 2 over all that. Which, remember, the phase shift is kind of like the idea of or it's very much just using the idea of a U substitution. So here we have 2 times the inverse Laplace transform of, if you thought about this, 2 over z squared plus 4. Kind of like that. But if you notice, it's 2 over a variable squared plus 4. That 2 over variable squared plus 4, that's sine of 2t. But because it has this shift, we throw the e to the at in front of it. So it's actually 2 times e to the 3t, because remember the sign changes, times sine of 2t. So doing the inverse Laplace transform here, when you're kind of when you're in the Laplace transform, like when you're literally in the S-plane, it is a lot of algebra. That's what you're dealing with a lot of the times. You're not going through and finding like all of our differential equations methods. You're almost just back in a world of algebra. So in this case, it was complete the square and then look back at a chart and go, oh, well, I remember that looks pretty much now like my sine of a function or sine of kt. But then you go, oh, but it's s minus 3. So that's actually that shift of a function that we talked about in 7.2 or 7.3. And so then you can just say, oh, well, now I can just go backwards from that, because I know that if I did the Laplace transform of e to the at times the function of t, that's just a shift of the Laplace transform of whatever that function was. So then read that sentence backwards. I know the function with a shift is this, so the original function is this. And it makes your life a lot easier. So you're able to get back to that original function without any issues. Now, here's one, speaking of issues. What is the inverse Laplace transform of this function? Not the nicest looking thing. This doesn't even look close. We can't complete the square. I mean, we have a cubic function, so definitely not going to work there. So this is where we run to a backup plan. Reaching back into kind of a Calc 2 tool, or a tool that was used mostly in Calc 2 with partial fractions. Which partial fractions gives you the different function pieces. And it gives you a way to break these apart. So now, if there were any multiplicities, we would have to take those into account, but fortunately we don't have any. Just if you need to review that, just look at partial fraction method and have that review handy if you need it. So what would end up happening, though, is we're trying to find and compare these coefficients of the numerator to the denominator, or we're trying to break this whole up into literally the sum of its parts. And you notice if you were to try and get a common or if you were to get a common denominator, what you would end up with is I would have a times s minus 1, s minus 6, and then I would have plus s, or b times s minus 6, plus b times s minus 6, and then plus c times s minus 1. And then we know the denominators are the same now, so then what you would do is you can compare 6s squared minus 13s plus 2. Now, there's a method that is referred to as, I believe the dude's name is Heaviside, Heviside. And what you do is you say, okay, instead of multiplying all of this out and trying to figure out, okay, what is A, what is B, what is C, you would do, or you could plug in your roots of the equation. Because this equation should balance, right? Which means if I plug in 3, it should be the same on both sides. If I plug in 4, it should be the same on both sides. The reason I say plug in the roots is, notice if I plug in 1 here, then this term goes away, or the A term goes away, and the C term goes away and only leaves B. So if I plug in 1, I end up with s, or 1 times 1 minus 6, and then I would also get 6s squared, or 6 times 1 minus 13s plus 2, and then I would have an equation that should balance out if everything goes correctly. So I'll show the example with B, and then you could try it for yourself. So if s equals 1, I get 6 minus 13 plus 2. And then that's going to be equal to b times 1 times negative 5. So negative 11. So yeah, negative 11 plus 6 is negative 5, which equals b times negative 5. So that gets you that b is equal to 1. So it's just a nice way to not have to do the coefficient matching. You're able to avoid any systems of linear equations, and it just makes your life a lot easier. So that method works here. You have to be careful. The reason I brought up the repeated roots is you have to be careful, because if you have, say, s squared in the denominator, you have to have a plus bs to take that into account. So that means if you try to plug in s was 0, you lose one of those coefficients. So you would have to do, you could do the Heaviside method for some of them, but then you would have to go back and actually plug in a value to find the others. And so a is equal to 1/3, c is equal to 14/3. And again, you would get those from the either partial fractions with the coefficient matching or doing the Heaviside method. Which means now we've reduced this problem to something a lot easier to look at. Because now I have the inverse Laplace transform of this sum, which means I also have, and if I factor some of these out, I get 1/3 inverse Laplace transform of 1 over s plus the inverse Laplace transform of 1 over s minus 1 plus it's linear, 14 over 3, like with this one. Inverse Laplace transform of 1 over s minus 6. So this is just going to be 1/3 times just 1/3, because 1 over s is just the Laplace transform of e to the negative t, which is the definition of the Laplace transform. Then this one's going to be plus e to the t, because it's got a shift, and then plus 14 over 3 e to the 6t, because it has a shift, but we now have the inverse Laplace transform, and in this case all it took was the use of partial fractions. So this is also kind of like dusting off all the tools in your bag to make sure that you can go through and say, oh, this one will work, so on and so forth. So by linearity, that was our Laplace transform. Now, just because I don't like myself, we're going to do one with a natural log. Oh boy. So natural logs aren't linear in this case. I can't just say, oh, the Laplace transform of the natural log is the same as the natural log of the Laplace transform. If only life were that simple. But what I can do, this is the nice thing, I can't really do some approximation for that. But can we do something more like our rational expressions with the partial fractions? This is where you have to be very clever, and I specify very clever. Remember, the Laplace transform of negative t to the n was, or times the function of t, was the nth derivative of that function. So to take advantage of those log properties, the natural log of s minus 3 over s squared plus 16 is the same as the natural log of s minus 3 minus the natural log of s squared plus 16. So what we can do is say, okay, well, now I'm going to take the first derivative of that, which the first derivative is 1 over s minus 3 minus 2s over s squared plus 16, which now our natural logs have disappeared, so hallelujah, that's good to see. And 2, we've split them up into something a lot more manageable. Because now, if you take a look at it, what we can do is break it apart and use our linearity. So what it means is I've done the first derivative, which means I'm not doing the inverse Laplace transform of f of t. I'm doing the inverse Laplace transform of f of t times negative t. This is the part where you have to be very careful. Which gives us, by linearity, nicely, this is 1 over s minus 3, so that's just e to the 3t, and then minus 2 cosine of 4t but, and this is the kind of crux, what did I solve here? I didn't solve for f of t. Currently what I have, because I'm kind of running out of room here, is I have negative t times f of t is equal to e to the 3t minus 2 cosine of 4t. Thus, in order to get my final answer of what f of t is, I have to divide both sides by negative t. So if I do that, then I end up with negative e to the 3t over t plus 2 cosine of 4t. And if you wanted to, you could write this all over a single t, but just to keep them separate, that's what I'll do. And so we have, in turn, a solved out Laplace transform. And the thing here that you have to be careful of is, like I said, we didn't solve for f of t. We solved for negative t times f of t. So in order to counteract that, make sure that you divide out whatever coefficient popped out. So if you run into like a natural log or something that looks kind of messy, you can always take the derivative and see, well, can I get rid of some of that popped up? Like for the previous problem, you probably don't want to do that derivative because that's just going to be one ugly chain rule that, or not chain rule, but quotient rule that's probably going to leave you with more work than when you started. So go over the homework, or this is the homework. Read over 7.4 again because this is a very important chapter. Because, again, the whole point of learning Laplace transforms is about being able to bring them back to a regular function. Because I don't really care what the Laplace transform is. I care what it is so I can get it back to my t domain so I can actually answer my differential equation.